Hey y'all, welcome back to Math Rescue. I'm Andre, your certified math coach. In this video, we're using Desmos to connect the graphical representation of a polynomial with the algebraic rule. I'll show you how to match up factors with x-intercepts and how to read end behavior directly from the equation. Once you see how the graph and the rule tell the same story, everything about polynomials is going to start to click. Let's talk about it. So we have two representations here. We have our algebraic rule, and then I've also graphed this exact same function f on the grid here. So our goal is to be able to connect these two representations. A big idea in high school mathematics is being able to go between multiple representations, being able to go between function rules, tables, graphs, ordered pairs, etc., and recognizing that these are all kind of showing the same thing dressed up in different outfits. So first thing we're going to do is we're going to take a look at the graph. And what we want to do is we want to grab the x-intercepts. So I have an x-intercept here, here, and here. Let me go ahead and record that. So we have x-intercepts at -2, 1, and 3. The reason why the x-intercepts are super important is because they connect back to the factors. And the factors directly tell us about the algebraic rule. In this case, this factor is going to give me x plus 2. This factor is going to give me x minus 1. This factor is going to give me x minus. If in your head you're asking if they go in opposite, they do. When we transform them into factors, they kind of look like they're changing signs. Once we have factored form, what we would do is we would take factored form, and through multiplication, we can actually end up and arrive at standard form. Standard form is this format over here. So what you would do is you would take those three binomials, 1, 2, 3, you'd multiply them out, and you would end up getting this as a result, that format there. So right there, you can see how just from x-intercepts, we can get the full equation, at least the majority of it, especially in simple cases. The next thing that we want to connect is end behavior. So for end behavior, and I'll come back and talk about zeros and ordered pairs in a second. But for end behavior, whenever we see x approaching negative infinity, that's talking about the left side of the graph. And whenever we see x approaching positive infinity, that's talking about the right side. So on the left side of the graph, I can see that the y value is just going perpetually down. I'm going to go ahead and say that f of x, which is a longer way of saying y, going to negative infinity there on the left. And here on the right-hand side, our y value is going up. So our y value is going to its infinity. All right. Let's say that you are in a situation where you only have the graph and you want to try to predict where the zeros and the ordered pairs are. One thing that you can do is you can look at the ordered pairs as they approach R0. So for example, if I kind of estimate this point here, this is happening at -2, -1. This point here, again, just kind of estimating. This is a little bit closer to 0 on the x-axis. So I'll say -1.9. And this is at +1. From this, because I went from a negative y value to a positive y value, I know that somewhere in here I had to have crossed the x-axis. There had to be a 0 in there. So if you're working with something like a table of values, you can make these observations by looking at how the values in the table are changing. If I see something like this, there must have been a 0 there. And when I say 0, that's another way of saying x-intercept. I'm Andre with Math Rescue. See you in the next one.